A few days ago, a fully wrapped mystery EV cruised down a Silicon Valley freeway like it owned the lane. It looked compact, tight, and purpose-built, and to anyone who's been tracking the whispers, it felt like the long-rumored entry-level Tesla finally stepping into the daylight. Timing, location, and the way it moved, all of it matters. When a prototype is out mixing with regular traffic, not stuck on a closed track, that screams confidence. It says the platform is far enough along that the team wants to gather real-world data, not just lab numbers. But here's the wild part. Even under that heavy camouflage, certain proportions and tiny bumps in just the right places hint at massive shifts in how this thing is built, powered, cooled, and driven. If accurate, what we're seeing could reshape how affordable EVs are engineered and assembled, and how quickly they charge, and how smart they can be without blowing the budget. Let's set the scene. For months, rumors have bounced around forums and group chats. Would the new low-cost EV use the same old formula with a cheaper battery and fewer features? Or was there something bolder brewing? This highway sighting doesn't give us the spec sheet, but the silhouette tells a story. The stance looks planted. The wheelbase, distance between front and rear wheels, seems generous for the car's overall length. The front overhang looks short, like the designers push the wheels close to the corners. And the side profile? It sits low and clean, almost as if the floor itself is doing more work than usual. The more you stare at the photos, the more one idea pops. This platform is not built the same way as the current lineup. Zoom in on the rear three-quarter view and look at the floor relative to the wheel diameter. To a trained eye, that relationship matters. Older EVs often have a distinct pack sandwich mounted between the axles. This looks different, more integrated, flatter, like the floor itself is the battery, not just a tray carrying one. That points to a direction engineers have teased for years, turning the battery cells into a true structural element of the car's body. Not just a structural pack, but possibly a cell-to-chassis approach where the individual cells are bonded directly into the floor structure. No separate, heavy housing. No big pack hanging under the cabin. Just energy storage and structure fused into one. Why does that matter? Because when you remove the pack casing and build the floor around the cells, you save mass, reduce parts, and stiffen the entire body. A lighter, stiffer platform helps everything. Ride quality, handling, safety, efficiency. In a crash, having hundreds of cells anchored into strong, continuous structures can spread loads more evenly instead of all that energy concentrating in pack mounts or flanges. In plain English, fewer big chunks to deform or fail, more distributed strength. Of course, that's not a free lunch. Making the floor out of cells comes with a minefield of engineering challenges. You need spot-on thermal control so cells stay in their happy temperature window. You need bulletproof electrical isolation so the structure can take real-world abuse and corrosion without any unexpected shorts. You need crash protection that keeps cells out of harm, sway without a traditional armored box around them. You need the right adhesives, potting compounds, and cooling pathways that can survive years of heat cycles, potholes, rain, and everything else a commuter will throw at it. Here's the kicker. If this prototype is truly running around on public roads already, it means those problems aren't just PowerPoints in a conference room. It suggests the big unknowns. Thermal expansion management across the whole floor, keeping cell compression uniform over time, isolating heat during fast charging, protecting the pack in a side impact, are far enough along that the team is comfortable learning at freeway speeds. Not done, not finished, prototypes evolve constantly, but real enough to put thousands of test miles under its belt. There are physical clues that back this up. Look closely where the camouflage meets the rocker panels. On older designs with a separate pack, you'll often see a subtle seam or lip, a structural interface where the pack bolts into the body. Here, the lower body surface looks smooth and continuous, like the floor and sides are a single, uninterrupted piece. That's exactly what you'd expect if there's no conventional pack flange because there's no conventional pack. If the cells are integrated into the chassis, you also unlock packaging gains. By ditching the pack housing and optimizing the cell arrangement for this one platform, you can fit more usable energy into the same footprint, or hit the same range with fewer cells. Engineers call it volumetric efficiency, and a cell-to-chassis approach can bump that by roughly 15 to 20% over traditional packaged packs. That's huge. For a car targeting around 250 miles of real-world range, a 15–20% improvement might be the difference between "we can hit the price point" and "we'll have to compromise somewhere painful." Fewer cells mean lower cost and less weight. Less weight means better acceleration, shorter braking distances, and more miles per charge. It's a cascade of small wins that add up. Now, charging. If you've looked at the camouflage near the charge port area and thought, "Hey, that looks a bit bulkier than usual," you're not alone. That extra volume could be hiding new power electronics and thermal hardware that support a higher voltage architecture, potentially 800 volts. Why chase higher voltage? Because it lets you push the same power with lower current, which means smaller, lighter cables, less heat, and faster, more efficient charging sessions. The trade-offs are real. The cells, inverters, connectors, and cooling systems all have to play nice at those voltages, and the thermal strategy needs to be dialed in to keep everything comfy during a rapid top-up on a road trip. But if they pull it off on an affordable platform, that changes the narrative. Suddenly, you're not waiting forever at a charger just because you bought the budget model. You roll up, plug in, and get back on the road at speeds people usually associate with six-figure EVs. That knocks down one of the biggest psychological barriers for mainstream buyers: time. Range anxiety gets a lot of headlines, but charging anxiety is often the real villain. If this car can do meaningful, repeatable fast charge sessions without cooking its battery or throttling speeds, it moves the goalposts in the entire affordable segment. Your road trips feel normal. Your errand runs are effortless. And the brand gap between starter EV and Halo EV starts to melt away. But the ripple effects go further. When the battery becomes part of the structure, manufacturing has to change too. Suppliers, adhesives, structural foams, cell formats, quality checks, everything gets rethought. You're not just validating a different pack, you're validating a new way of building cars. That means putting the entire process under the microscope, making sure bond lines are precise, thermal pads seat perfectly, cooling channels are consistent, and any imperfect part gets caught before it ever gets near the assembly area. And because serviceability matters, they'll need procedures for safe repairs if the car takes a hit. Can a floor module be sectioned? Can localized damage be repaired without tearing apart the entire underbody? The existence of multiple road-going prototypes suggests these questions aren't theoretical anymore. There's an ecosystem forming around this build method: materials, tooling, inspection, and field service, all learning in lockstep. Quick gut check. Do you think turning the battery into a structural element is the next big leap for EVs? If you're on board with that line of thinking, drop the word "structural" in the comments so I know you're vibing with this direction. All right, sensors, this is where things get spicy. Take another look at the roofline, especially where it meets the windshield. See those subtle bulges and little surface breaks peeking through the camo? That's not sloppy wrapping. Those shapes are often dead giveaways for embedded hardware, cameras, lighting for sensors, or mounting bosses to keep things stable. And the pattern doesn't T-map perfectly to the camera layout we've seen before on current production vehicles. So, what could they be testing here? The obvious answer is more cameras, or cameras with different fields of view that help depth perception, occlusion handling, and lane tracking in messy urban scenes. But there's more. The spacing and angles you can infer from the front fascia suggest we might be looking at stereo vision up front. Two cameras calibrated together to create depth maps the old-fashioned way: parallax. Stereo has some lovely benefits for an affordable car. It's relatively cheap compared to fancy sensors, It gives you reliable distance measurements in a lot of everyday conditions. And it eases the computational load compared to extracting depth from a single camera stream using heavy neural nets. Less compute means less cost and less heat. That critical if you were trying to ship at a price the mass market can stomach. Now, before anyone jumps into a sensor war in the comments, yes, there's a long-standing debate about whether you should lean on cameras only, or mix in radar, or even add LiDAR. The company has been vocal about a vision-first path, and they've even pulled radar from production cars in the past. But testing other configurations is smart engineering. You don't prove your approach in a vacuum, you compare it to baselines. It's entirely possible this prototype is running extra sensors temporarily, not for production, but to gather reference data and define edge cases. Want to know how well Pure Vision handles sleet at night on a reflective road? Run it side by side with radar or LiDAR, record everything, and use those comparisons to make your model better. Testing something doesn't mean shipping it. Let's talk computing. Autonomous features live and die on the efficiency of the perception-to-action pipeline. Cameras stream raw pixels into a system on chip. The neural nets chew through that fire hose, estimating depth, segmenting lanes, spotting vehicles and pedestrians, reading signs, predicting intent. Then planning decides what to do: accelerate, brake, change lanes, hold back, while control systems carry it out smoothly and safely. To make that work in an affordable car, you need hardware that punches above its weight, not just brute-force chips that cost a fortune and drink watts like a thirsty camel. Every dollar and watt matters. That's why highway testing is so juicy here. Highways are cleaner than city streets, but still brutally demanding for autonomy. High speeds, quick merges, tight cut-ins, sudden debris, reflective surfaces, and tons of edge cases at dawn and dusk. If this prototype is racking up miles on production intent compute, meaning the hardware they hope to ship or something very close to it, then every hour out there is validating not just the sensors, but the entire software stack. It's proof that the system can process, plan, and act in time to be safe. It's also gold for training data. Real traffic throws curveballs no simulator can dream up. There's a strategic layer, too. Launching with basic driver assistance and increasing capability over time via over-the-air updates is a well-known playbook now. But doing it on a cost-constrained platform is a different sport. The hardware you build in today has to be robust enough to support features your AI team will invent tomorrow. That means choosing camera resolutions, fields of view, thermal design, memory bandwidth, and redundancy, with a future you can't fully see. That's a balancing act. Don't overbuild and blow cost targets, but don't paint yourself into a corner. Sensor placement is part of that insurance policy. Those little bumps and recesses on the roofline could be designed to accommodate second-generation sensors later without redesigning the sheet metal. Maybe you launch with a certain camera pair and swap in higher-resolution modules for a mid-cycle refresh. Maybe you reserve space for an internal radar reintroduction if the data says it's worth it. You can't add that flexibility after the fact without serious retooling. Building it in early costs more upfront, but pays off massively if the field data points you toward a different mix. Calibration is another reason to get these prototypes on real roads. Stereo rigs need micrometer-level alignment. Cameras mounted to thin roof panels can drift with heat, vibration, and the simple realities of doors slamming for years. If the manufacturing process includes pre-aligning whole modules before final assembly, calibration can be locked in earlier and verified with automated test rigs. That's the kind of detail you iron out now, not a month after customers get cars. While we're here, let's acknowledge safety engineering. You can't talk driver assist without talking redundancy and fault handling. Affordable doesn't mean bare minimum. If the plan is to lean on vision, you still need robust fallback strategies. How do you brake safely if a camera fails? What happens in a power brownout? Is the low-voltage system moving to 48 volts for better efficiency and cleaner power delivery to sensors and ECUs? Do you have independent power rails for critical cameras? None of that is flashy, but it is the difference between a neat demo and a production system you trust with your family on board. Can Vision First autonomy scale to millions of cars without giving up capability? Or will sensor fusion win out? I'm genuinely curious where you stand. If you think vision is the path, type vision in the comments. If you're Team Fusion, tell me why. Now, the proportions of this thing. They're the kind of subtle clue engineers can't hide with vinyl wrap. That short front overhang and stretched wheelbase are more than a styling flex. They read the fingerprints of a new way of assembling cars, something the company has been teeing up publicly, an unboxed process where big sections of the car are built in parallel and married together late in the game. Instead of dragging one half-finished car down a long line while dozens of teams swarm it, you build whole modules independently. The front corner with its crash structure, motor cooling and suspension, the rear drive unit and suspension, the interior capsule, the structural battery floor, and then snap them together with precision. Why go to all that trouble? Because it kills the slowest station bottleneck that haunts traditional assembly lines. On a classic line, your output is limited by whichever station takes the longest. With parallel modules, each subassembly is built and validated at its own pace. If your rear module team gets ahead, they can bank inventory. If your interior capsule needs an extra calibration step, it doesn't hold up the whole plant. At the end, you join everything, run a tight set of end-of-line checks, and ship. That approach unlocks other optimizations. In a traditional build, workers and robots need access to everything from weird angles, which forces designers to keep certain spaces open during early steps. But if the front module is built offline as a self-contained unit, you can pack it tighter, integrate the cooling loops and heat pump right into its structure, embed active aero shutters to manage drag and cooling air, and mount the suspension in ideal locations without worrying about assembly reach. That is how you end up with the wheels pushed far forward. The entire front corner is a module that slots into the body like a cartridge. There are external hints that this is exactly what's happening. If you look at where the camouflage changes grain or breaks vertically, you can sometimes spot likely module seam lines. These are places where, under the wrap, the real body has clean separation planes. That's not guaranteed, but it's a known tell in prototype land. All right, let's take a closer look at what's really going on with modern EV manufacturing, because some of the choices here are incredibly telling. Peeking through the wheel wells, the geometry suggests a multi-link setup at the rear. That's more complex than the simple torsion beams you'd expect in a so-called bargain car. So why go fancy on a budget model? It's all about the assembly process. If you're building the entire rear module as a pre-validated subframe, with control arms, bushings, dampers, and even brakes all mounted and aligned, you can drop it into the car in one single shot. The extra component cost is completely offset by the time saved and the tighter, more repeatable quality. And as a driver, you feel that every single day through better ride comfort and more poised handling. It's a win-win. Now, let's talk numbers without quoting any specifics. The claim is that this method can shrink the factory footprint by something like 40% and massively speed up builds. This isn't just a PR line. If you replace long sequential assembly lines with parallel module cells, your whole plant layout tightens up. Material flow becomes shorter. You need fewer conveyors. Energy use drops. Less work in progress piles up on the floor because each module cell feeds the final assembly point just in time. When cost per unit is everything, this operational efficiency is the real game changer. This unboxed method also brings a new level of precision to crash engineering. Instead of tuning an entire car body piece by piece, you can design the front and rear crash structures as complete, tested units. They can be validated repeatedly on dedicated rigs before they ever meet the rest of the car. That consistency is crucial. It makes crash test results more predictable from one car to the next and simplifies quality control. It also pairs beautifully with the trend of large castings, those front and rear, mega or giga castings that replace dozens of stamped and welded parts with one giant die-cast structure. Combine those with a structural battery floor, and you've connected incredibly stiff elements with clean, simple interfaces. Add some high-strength adhesive bonding at strategic joints, and you get a body that's both lighter and stronger, with far fewer welds. The thermal management system appears to be tightly integrated as well. Look at the lower front openings on these new designs. They don't just scream "big radiator forever." The shapes hint at configurable airflow, with active shutters that only open when needed. This cuts down on drag at high speed but can also feed cool air to the radiators, the heat pump, or the battery during a fast charge. When you build the entire thermal system as part of a front module, not as an afterthought, you gain incredible control over coolant line lengths, sensor placement, and insulation. That translates to faster cabin warm-ups in the winter, stronger air conditioning in the summer, and better efficiency all year round. Even quality control gets a complete overhaul under this philosophy. Instead of one single massive end-of-line inspection where you're frantically trying to find every rattle and mistake, each module can be tested deeply on its own. You can run NVH, that's noise, vibration, and harshness, checks on the rear suspension module before it ever meets the car. The cooling loops can be pressure tested at the module bench. Cameras and sensors can be aligned and calibrated in a perfectly controlled jig. Then, you just need a final, much shorter verification after the main modules are all married together. And if something does fail at that last step, you can often just swap the faulty module rather than performing complex surgery inside a half-built car. This could also make service and repair much easier in some cases. Imagine a rear-end crash that damages the suspension pickup points. Replacing a complete, pre-aligned rear module could be way faster and more consistent than trying to rebuild that geometry inside a wrecked unibody shell. Insurance companies love predictability, body shops love bolt-on solutions, and owners, well, we just love getting our cars back quickly. Now, not every fix will be modular, but for common collision scenarios, the option could be a huge benefit. So, will this modular assembly drive the next big drop in EV costs without gutting the features we love? If you think building in parallel is the future, do me a favor and write modular down in the comments. Let's zoom out for a second and put all these threads together. You've got a cell-integrated floor for lighter weight and more range per dollar. You have a higher voltage architecture that allows for fast charging, even on cheaper models. You get a sensor layout that's been tuned for cost-effective autonomy. And underpinning it all is an assembly process built around these parallel modules. When you do all this, you start to see the grand strategy. This isn't just about taking a premium EV and stripping out features until it's cheaper. This is a fundamental, design-from-scratch approach for the mass market. And when you design this way, the trade-offs completely shift. You can keep the driving dynamics sharp because the underlying structure is incredibly stiff. You can keep the cabin space generous because the wheelbase can be stretched and the floor is thin. You can make long road trips feel normal because the charging system is robust and the thermal system is smart. And you can ship continuous software improvements because the hardware was chosen with tomorrow's algorithms in mind. Of course, there are still some unknowns. The serviceability of a structural battery pack is not a trivial matter. If the floor of the car is the battery, what happens if you get deep damage from a curb or a nasty side scrape? Are there sacrificial rails and shields built in? Can sections of it be repaired? Engineers are well aware of these questions, and the answer is rarely one size fits all. We can expect to see robust underbody protection, clever load paths designed to direct impact forces, and careful isolation so that damage doesn't propagate where it shouldn't. Expect detailed service manuals that tell technicians exactly how and where repairs can be made safely, and when a full module swap simply makes more sense. This is the future unfolding right in front of us. Thank you so much for joining me on this deep dive. If you found this as fascinating as I did, please hit that like button and consider subscribing for more content just like this. See you in the next one. Hey everyone, and welcome back to the channel. Today, we're diving deep into some fascinating spy shots that just hit the internet. What you're looking at isn't just another camouflaged car, it's a rolling blueprint for the future of affordable electric vehicles. So, grab your coffee, get comfortable, and let's decode what these pictures are really telling us. First up, let's talk about something that matters to every EV driver: cold weather performance. Imagine trying to fast charge your car in the middle of a blizzard. That's the ultimate test, right? This prototype seems to be taking that challenge head-on. We're talking about the possibility of an 800-volt charging system, which is usually found on high-end models. But the real magic is in the thermal management. A clever heat pump, smart coolant routing, and a solid preconditioning strategy are absolutely critical. Look closely at the photos. See that extra bulk around the charge port and the front of the car? That camo could be hiding the advanced thermal hardware needed to make winter road trips completely painless. Now, let's address the elephant in the room: the price. We're not going to guess at numbers, but here's the reality. To hit an aggressive price point while still offering decent range and modern driver assist features, automakers can't just rip out everything you expect in a new car. The savings have to come from somewhere deeper, from the very way the car is designed and built. And that's why all these details are so important. If you can build cars faster in a smaller factory, if the body is made of fewer, larger, stiffer parts, if the battery gives you the same range with fewer cells, and if the computer runs cooler using less silicon, then your costs drop significantly. That's how you make the business case work. That's the real game being played here. The potential impact on the entire auto industry is massive. Other car companies have explored concepts like cell-to-pack or even cell-to-body battery designs. We're seeing more 800-volt systems pop up in premium EVs, and things like modular assembly and massive single-piece castings are gaining traction. But the truly difficult part? Bringing all of these innovations together in a car that's actually affordable and can be produced in high volumes. If this prototype is what it looks like, a validation of the entire package, from its structure all the way to its software, then we are literally watching the puzzle pieces lock into place for a new era of EVs. Let's shift our focus to the interior for a moment. A thin, structural battery floor combined with wheels pushed out to the corners is a classic recipe for fantastic packaging. This design gives you a lower floor, which means smaller drivers can feel more confident behind the wheel without sacrificing headroom for taller passengers. You also get the long wheelbase of a larger car in a compact body, which typically results in a smoother, more stable ride on the highway. And if the entire interior, seats, dashboard, airbags, wiring, even the glass, is built as a single, separate module and then installed into the car, that often leads to a huge improvement in fit and finish because workers and robots have clean, easy access. Less twisting and turning on the assembly line means fewer scuffs, fewer loose clips, and fewer annoying rattles down the road. Another area worth watching is the low-voltage system. A modern electric car is packed with sensors, cameras, heaters, pumps, and computers. And moving to a more advanced 48-volt low-voltage architecture can significantly cut the electrical current needed, which allows for thinner, lighter wires and improves overall efficiency. It also provides cleaner, more stable power to all those critical sensors we talked about. If that's part of the plan here, it fits perfectly with the overall theme of creating lighter, more efficient systems throughout the vehicle. I know what some of you are thinking. What about the long-term health of a battery that's part of the car's structure? Heat is always the enemy of batteries, and gentle, slow charging cycles are still your best friend. The strategy here will rely heavily on precise coolant channels, high-quality thermal interface materials, and intelligent software that preconditions the battery pack before you hit a fast charger or decide to race up a mountain pass. The first cars off the line will teach the engineering team a lot, and that's perfectly fine. The real beauty of a software-defined vehicle is how quickly those lessons can be applied. What this prototype learns on the road today can inform a software update you download to your own car just months later. So, what does this all mean? We have a camouflaged compact car that seems to follow a very clear philosophy. Make the battery do double duty as part of the structure, make the body simpler and stronger, make the assembly line faster and more flexible, and make the driver assist as capable as possible without breaking the bank on hardware. It's not about one single standout feature. It's the brilliant combination of all these ideas working together. That's what makes this sighting on a busy California highway so exciting. We're not just looking at a new car model. We're getting a sneak peek at a completely new rulebook for building budget-friendly EVs. If you've stuck with me this far, you are definitely my kind of car nerd, and I really appreciate you being here. I want to hear what you think is the biggest game changer. Drop a comment below with the word structural if you think the battery as frame design is the most important innovation. Type vision. If you believe the camera-first approach to driver assistance is the key to affordability. Or write modular if you think the unboxed assembly method is the real secret sauce. Let's see which idea gets the most votes. Now, let's be realistic about the timeline. A prototype on public roads doesn't mean it's hitting showrooms tomorrow, but it does tell us that the project is well past the early, experimental stages. The body proportions look nearly final. The cooling and charging systems seem far along, and the sensor layout is likely undergoing its final tests. The software will continue to evolve right up until launch and beyond. The fact that we're seeing multiple test cars out in the wild, not just a single one-off, suggests this program is maturing very quickly. Imagine walking into a dealership as a first-time EV buyer. The entry-level model isn't a stripped-down compromise. Instead, it's a car that's quick to charge, easy to live with, surprisingly roomy for its size, and feels confident on the highway with smart driver assistance. That's how you win over the next wave of EV adopters. Not with a basic Econobox, but with a cleverly engineered car that makes people wonder, why would I ever need to pay more? That's the quiet revolution this prototype is hinting at. And these real-world tests are a great reminder for all of us to keep our eyes peeled. Those bumpy, boxy-looking cars with mismatched wheels and taped-up panels? They're postcards from the future, whispering about what's next, if you just know how to read them. Let's do a quick recap before we wrap up. We likely saw a structural battery floor, possibly even a cell-to-chassis design, that cuts weight, adds stiffness, and extracts more range from fewer cells. We saw hints of high-voltage charging, potentially 800 volts, suggesting faster and more efficient top-ups. The sensor layout points to a cost-effective autonomy system with stereo vision cameras up front, and the proportions scream unboxed assembly, with large castings and pre-built modules that can be put together like building blocks. Combine all of that into a compact car with a long wheelbase and short overhangs, and you have a vehicle designed from day one to be affordable without sacrificing the features people actually want. If you had a good time geeking out with me today, do me a huge favor and hit that like button so more people can find this analysis. Subscribe if you want more deep dives into automotive engineering in your feed, and tap that notification bell so you don't miss the next prototype we decode. Don't forget to light up the comments with structural, vision, or modular, and tell me why you picked it. Until the next sighting, keep your eyes on the road. Those camouflaged cars aren't hiding the future. They're announcing it, one highway at a time. Thanks for watching.